Hello everyone, welcome to our first video in the engineering mathematics course. So today in this video we will start talking about linear systems and matrices. So here is a system of linear equations. Usually we will denote our variables with x1, x2 all the way to xn, assuming that we have n number of variables. And the coefficients will be denoted by the constants a1, a2, an. And on the right hand side, in a linear equation, we will have the constant b. So this is a linear equation that you are already familiar from your previous courses, actually. Here are some examples for our linear equations. For example, 2x1 plus 3x2 minus x3 equals to minus 1. So this is a linear equation, and as you see, we have only linear terms in x1, x2, and x3. Okay, what about a not a linear equation or non-linear equation? For example, we might have this example here. This is not a linear equation because we have these x terms cross multiplied. So you can think this as a cross term, or we might have some higher order terms in x1, x2, or x3. Then we will call this not a linear equation. And in the second example here, as you see, we have the cubic power in x2, so this is no longer a linear equation. And we will have systems of linear equations if we have more than a single linear equation. And we can have x1, x2, again xn. We have these n number of unknowns, and in total we might have these m number of equations here. So we have m equations here with all these coefficients are constant terms, and again these right hand side values are given by b1 to bm. Again, these b values are constant. Assuming these coefficients are all constant, we have a system of m equations, and each equation is a linear one. So in this type of problem, if the system has a solution, it is called as consistent. Otherwise, it is called as inconsistent. So this is the keyword, consistent versus inconsistent, depending on whether we have a solution or not. In the system of equations, if we have all these right-hand side values are equal to 0, we call this as a homogeneous system. So it's a special case of the general system of equations. And as you see, these terms, if all of them are equal to 0 on the right hand side, then it's a homogeneous system. And for this system, notice that, if this is the homogeneous system, we can always solve this system by the so-called trivial solution. And the trivial solution means all the x values are equal to 0. So this is always a solution, which is called as a trivial solution. So the solution without all x being equal to 0 is called as the non-trivial solution. Another term here that we would like to introduce is the so-called equivalent systems. And here's an example. We have x minus y equals to 7, 2x plus 3y equals to minus 6, and then here actually we can solve this system, and the solution will be, you can verify this easily, right? For example, you can multiply both equations by 3. So this will become 21. And then if we add these two equations together, right, 21 minus 6, 15, 5x equals to 15, x equals to 3. So you can easily obtain the solution in two unknowns, two equations system here. And we can also have an equivalent system that will also have exactly the same solution for x and y. If these solutions are the same, these two systems here, they are equivalent to each other. And similarly, we might have, let's say, three unknowns, three equations. Here, this system is denoted by star. And actually, these three equations, three unknown system, we can do some operations. So representing the first equation by E1, represent the second equation by E2, and the third equation is represented by E3. So if we do this operation, multiply the first equation by -3 and then add it to the second equation, and we can assign this sum to the second equation. Alternatively, you can do another operation. You can multiply the first equation by -2 and then add to the third equation. So that will be your new equation 3. So that means what we obtain in this double star, a single star and double star, these two equations are equivalent. Actually, we can scale one of the equations and add or subtract to the other equation. So these are legitimate operations in a system of equations, and it's not going to change the solution of the system because we are doing the scaling, for example, both on the left side and right hand side, or we might add left side with another equation, and then similarly the right hand side is also following the same operation. So the result, the solution of the system is not going to change. Actually, this is why later on we will talk about the Gaussian elimination method to solve the system of equations by doing this type of operations in our equations. Here's another example. If we want to solve this system, and the system is given here, okay? You have two equations and two unknowns. So what can you do? For example, we can write this as x1 minus 2 times x2 equals to 8. Obviously, this is the same, right? I mean, swapping the order of the equations doesn't change anything in the system. I mean, I can assign the second equation as the first equation here, and I can assign the first equation as the second one. And then we can, let's say, for example, multiply the first equation by -5. So if I multiply this x1, this is going to be -5 times x1, right? And then this will be plus 10 times x2, and this will be -40. If I do this operation, multiply this by -5 and then add it to the second operation to assign this result as the second equation of the system. So what do we get? We get this -5x1 plus 5x1. So actually that will cancel, these two terms will cancel each other. So you have 10x2 plus 3x2. So that's going to give us 13x2 here. And then here, -40 plus 1, you get -39 as a new updated second equation. Okay? And from here on, you can solve this x2 equals to -3. and then basically use this result in the first equation to obtain x2 and x1. And this is a unique solution. We have two equations and two unknowns. Basically, that will give us a unique solution. We have some more examples. You can easily go over these. We can easily go over these examples quickly. Again, you have two equations and two unknowns system. And notice that I can multiply the first equation by -3 and then add with the second equation. Now, if I do that, what do we get is basically the x1 plus 3 times x2 equals to 2. That's our first equation, okay? But in the second equation, notice that you will get 0 equals to 11, but that's a contradiction. So we denote the contradiction by this kind of symbol usually. Okay, so this will be a contradiction, and therefore there is no solution for this system. That's because these two equations are inconsistent with each other. I mean, as you notice, if we multiply this by 3, so you will get 3x1 plus 9x2 equals to 6. But the same equation cannot be equal to 6 and 11 at the same time. So this system has no solution, obviously. In another example here, you can consider again x and y. We have two unknowns. The first equation equals to 2. Second equation equals to 6. Sorry, the first equation equals to 4 here and 6 in the second right-hand side. So now I can simplify these and I can write this as 3 and this becomes 2, right? X plus 3y equals to 2, that's my first equation. But actually the second equation, again, simplify by 3, so this is x plus 3y equals to 2 as well, which is the same equation in, just in different representation. But these two equations are the same. So we have two unknowns, but actually, essentially, we just have a single equation. That means we have infinitely many solutions. We are free to choose x and y. The next thing to consider is now let's look to the geometric interpretation of a system of equations and try to understand when this system has a solution or when it has infinitely many solutions. Okay, so it is going to be quite straightforward. Suppose for simplicity we have two equations and two unknowns. Our unknowns are x and y, okay? And these are the coefficients a11, a12, etc. So each equation here represents a linear line, okay? Because we have linear equation, it's a line in the Cartesian space, 2 by 2 space. So the thing that we can do is draw these lines for each equation and then analyze what are the potential situations. So if I draw two lines, as you know from calculus or other earlier courses, I think that's clearly something you already know. But if we have two equations, what are the three possible cases? Case 1, we have an intersection. So there is an intersection point of these two equations. Case 2, these two equations might be parallel to each other. I mean, these lines might be parallel to each other, so they never intersect. And in this case, there is no solution. And as you see, for example, one equation is x plus 2y equals to 1. The other equation might be x plus 2y equals to, for example, 5 over 2. Or 2x plus 4y equals to 5. So that's a shifted version of the first equation, meaning that these two lines are parallel to each other, so they never cross. If they don't cross, they don't have a common point, they intersect, then this implies there is no solution to this system. And the third possible outcome, as I mentioned, there are only three potential outcomes. Possibilities are only three. Two lines can be parallel, they can overlap. The third case is the overlap. In other words, two equations are the same, so there is essentially only one equation effectively. And the first case is that they really have an intersection, so there is a unique intersection and unique solution. And as you see here, the intersection is infinitely many because all the points are actually in the intersection. So there is infinitely many solutions in this case, in the third case. In the second case, there is no solution because there is no intersection. Now, in this part, we will start to talk about the Gaussian elimination method, which is going to be the method that we use to solve a system of equations. Here is the notation for our matrix representation. Remember that we have some coefficient matrix that represents all these constant coefficients in a system that we want to solve. And we can also briefly denote this. The element of this coefficient matrix A is represented by Aij terms. Of course, these J's, the index I represents here the 1 to n number of, basically, this is we have n number of variables, okay, that's the variables, and we have m number of equations. So this is for the variables. And we have m here, number of equations. That's the number. Okay, it's a bit difficult to write like this, but I think this should be clear now. And immediately we can consider some examples, like A. Suppose this is our coefficient matrix, or we might have a matrix A like -1, 2, and 3. In this case, it's a column matrix. And here another example with matrix B, where this is called as a row matrix. So here we need to be a little familiar with the linear algebra terminology. So we can go over these terminology slowly and make sure you can follow the matrix algebra, this linear algebra terminology. So before we can we can apply the Gaussian elimination. Let's introduce some matrix operations. And in the matrix operations, for example, summing two matrices, A and B, we have matrix A and matrix B. And if the dimensions of these two matrices are the same, n by m, then we can sum the element-wise all the terms in this matrix as a plus 1, a plus b. Another example, suppose we have the matrix A as 2 by 3, and we have matrix B also a 2 by 3 matrix. Then if we sum A plus B, then for example this 3 will be summed together with this 4, okay, and then similarly this 0 will be added by -3, and this minus 1 added together with 6, we get this 5 here, right? 0 plus minus 3, we get minus 3. And then 3 plus 4, we get this 7 as a result. Another important operation is multiplication with a scalar. So when we multiply a matrix A with scalar, so our scalar is denoted by this C. So that means each element is multiplied with the same scalar. Okay? Here's an immediate example. This is your matrix A. And if you multiply this matrix by minus 2, that means every element is multiplied by minus 2. Next, subtraction. In subtraction, basically, actually it is identical to the summation operation. There is not much difference because subtraction is also summing A and B multiplied with the minus 1. Actually, this is also a summation operation, but we have minus 1 multiplied with B. Multiplication. In multiplication, again, you need to make sure the dimensions match. If we have m by p matrix A, and if we have p by n matrix B, then the multiplication will give us m by n matrix because of these dimensions. And here is how we do the matrix multiplication. In matrix multiplication, you will consider row by row and multiply with the columns in the same order for the second matrix B. And once you multiply all these terms together with the first column, second column, all the way to the nth column, that will give us the new matrix that represents the multiplication of these two matrices. And here, this is the explicit summation for multiplying two matrices. Here's another example. Suppose we are given these two by 2. Matrix A is 2 by 2, and matrix B is also 2 by 2. That means we can multiply these two matrices with each other because both of them are 2 by 2, as we can see. So whenever we multiply A and B, the result is also going to be a 2 by 2 matrix. And how can we multiply that? Multiply this row with the column. So we get 2 minus 3. And then 2 times 5 minus 7. This is 10 minus 7. Here, minus 4 times 1 plus 9. So this is 5. And then you have minus 4 times 5. That's minus 20. And then plus 21, that's equal to 1. So this gives us the result of A times B in this example to demonstrate matrix multiplication. And similarly, you can also consider B times A, but you will notice that A times B is not equal to B times A in matrix algebra. This is different from the regular multiplication of two numbers. They are commutative, but here we cannot change the order of A times B into B times A. The order is not the same. Two matrices are equal to each other if Aij equals to Bij. For all the terms in the matrix, then you can say these two matrices are the same. And here we have we have the here we have the matrix B and A. So if x equals to minus 5 and y equals to 0, t equals to 2, we have a equals to b. So this is the parameterization we use here, x, y, and we have the t. So for example, x equals to minus 5, y equals to 0, and t equals to 2, then we can say these two matrices are equal to each other. Here are some basic properties of matrix operations that you should keep in mind, because we will be using these operation properties quite often. Here's a small exercise you can try. So the exercise is asking to show that a times b times c is same as a times b and then times c. Here's another two different exercises. In this exercise, similarly, we want to verify and calculate a times b versus b times a. So you can also easily check if these two are the same or not. And again, similarly, we have a times b versus b times a. You can check these. For example, a times b. What is the dimension of a? That's 1 by 2. What's the dimension of b? It's 2 by 4. So that means a times b is okay. It is defined. But what about b times a? So b times a this is 2 by 4 times 1 by 2. And 1 by 2. So that means actually b times a is not defined. This is not defined. But a times b, it is defined, right? So it's not the same. A times b and b times a are not the same thing. They are quite different from each other. So systems of linear equations in matrix notation. As you see, we can represent this system of equations in matrix notation using our coefficient matrix A, and we have the variables denoted by X. Here's another example. So in this example, we have the system. These are our coefficients. x1 minus 6, x2 equals to 3. So how to represent this, first of all, in a matrix notation, in the matrix notation. Representing the system is not too difficult. You have minus 2, 3, 1, minus 6, and then x1 and x2. And then on the right-hand side, we have minus 6 and 3 as the right-hand side of this equation. Basically, we can represent this system using the matrix notation A, X, and B. Okay, so this part now we can introduce our augmented matrix. And augmented matrix simply means I can add the right-hand side of my equations in the coefficient matrix. So by adding this column, my coefficient matrix becomes the augmented matrix, denoted by A is augmented by this B. Okay, and B is the right-hand side that we can write with these constant coefficients. Another example, this is also an augmented matrix. We have the coefficients minus 2, 3, 1, minus 6, and then these are the right-hand side values that are captured together in the same augmented matrix representation. Here's the definition. Applying finite number of row operations, we obtain an equivalent matrix. And the next theorem tells us that if two systems of equations have the same augmented matrix, then these two systems have the same solutions.